In this video, we are going to talk about naive Bayes classifier. Naive Bayes is a probabilistic classifier. So before we start, let's do a quick review of probability concepts you will need. Suppose you have 3 bits of information. 1, that 68% of US adult population is obese or overweight. 2, 15% of those who are obese or overweight suffer from type 2 diabetes. And that 12% of US adult population suffers from type 2 diabetes. So my first question to you is, what is the probability of a population suffering from type 2 diabetes? Or to say it another way, what is the probability that someone in US suffers from type 2 diabetes? And second, what fraction of US adults who are suffering from type 2 diabetes is obese or overweight? Take a moment, pause the video, and work out solution for these 2 questions first before you move on. We will talk about the solution next. Okay, so let's think about the first question. What is the probability of someone in the US suffering from type 2 diabetes? Well, actually, this is just a different way of saying this third bit of information that you have up there. If 12% of US adult population suffers from type 2 diabetes, that means of everyone in the US who is an adult, 12% suffer from type 2 diabetes. So probability of someone in US, an adult in US, suffering from type 2 diabetes is 0.12. Right? So that was an easy one. Let's look at the second question in more detail. What fraction of US adult population that is suffering from type 2 diabetes is obese or overweight? Well, this is not the same as the second bullet up there. That says 15% of those who are obese suffers from type 2 diabetes. This is kind of asking the reverse question, right? What fraction of those who are suffering from type 2 diabetes is obese or overweight? So let's solve it. I'm going to solve it using random variables so that I can kind of bring in the concepts of probability. So let there be kind of 2 random variables that we define. A is a random variable that denotes if somebody is obese or overweight. So probability of A, that means probability of this event happening, is 0.68. That is from the first bit of information. Let B be this variable that denotes someone who's suffering from type 2 diabetes. So probability of finding someone who suffers from type 2 diabetes is 0.12. Then you could solve it in 2 different ways. One, the probability style, and the other one is using this 2 by 2 confusion matrix that we have seen in earlier videos. How do you solve this? So suppose you have been given numbers as 68% and 12% and so on, right? So suppose you're talking about 1,000 people. Then this first bit of information that says 68% is obese or overweight would mean that 680 of 1,000 are obese or overweight, right? And if 680 out of 1,000 are obese, then 320 are not obese or overweight. Okay, the second bit is about 12% of population suffering from type 2 diabetes. So of 1,000, 12% will make it 120. And that means 880 don't suffer from type 2 diabetes. Great. Then you have this third bit of information. And that is saying that if someone is obese or overweight, then the chance that they are type 2 diabetic is 0.15. So that is written in probability as probability of B, this event of somebody suffering from type 2 diabetes, given A. That means that somebody is obese or overweight. So given you are obese or overweight, what are the chances that you are suffering from type 2 diabetes? So that means of the 120 that, of the 680 that are obese or overweight, 15% suffer from type 2 diabetes. So of 680, 15% is 102. And that means that 578 don't suffer from type 2 diabetes. And then you can fill up the rest of the cells. If 102 of 120 who suffer from type 2 diabetes are obese, then 18 are not. And 302 would be those who are not obese or overweight and don't suffer from type 2 diabetes, right? Once you have filled this one up, even the way I was saying it, you would have kind of realized that what you are asked now is probability of someone being obese if they are type 2 diabetic, which means that you're talking about 102 divided by 120, and that is 0.85. So the answer to the question is 0.85, right? So 85% of those that are type 2 diabetic are obese. You can do this another way without really actually filling up this table, and that would be using Bayes rule. So Bayes rule is saying that if you have probability of A given B, you can find that answer by seeing what is the conditional probability of B given A times probability of A divided by probability of B. Another way to say that would be probability of A given B is the probability of both of them occurring together. That's probability of A comma B, the joint probability, divided by probability of B. Okay, so there are just two ways of saying the same thing. And in that case, then these are the three factors that are given to you. So probability of B given A is 0.15, probability of A is 0.68. So multiply the two, divide by 0.12. That's probability of B, and that's 0.85. The same answer that you got the other way. Great. So you see this idea of random variables, about conditional probability and Bayes rule. Good. Now, why is that important in naive Bayes? How does it come up? So let's kind of go back to that. Instead of two factors, A and B, let us now consider n features, right? So suppose X, one of your data instance, is represented by n features, a set of attributes x1 to xn, and y is class label which is from one of these classes, y1 to yk. Usually in a binary classification task, the capital Y has only two elements, yes or no, or 0 or 1. So it will be just y1 and y2, right? If it is more than 2, then it's a multi-class classification problem. Then in a probabilistic view, there are two kind of terms that you should know of. One is called a prior probability. Prior probability means what is the probability of a particular class label without really knowing anything about the data instance. So prior probability in our set is probability of y is y1, the first class, or y is y2, the second class. So without really knowing about the actual instance coming in. So an example of that from our previous case was just overall in your population, how many are suffering from type 2 diabetes, right? Or how many are obese or overweight. If those were your labels, then just the probability in the general sense, without really knowing about a particular person, would be called prior probability. The second term that you should know is posterior probability. And posterior probability is, again, probability of this class, or probability of a class being y1 given x. So now that you know the features of this data instance x, what is the new probability there? So in the previous example, it was if you know that somebody is type 2 diabetic, what is the probability that they are obese? So that will be probability of obese given type 2 diabetic. Okay. In the classification sense, it is probability of output label y given the data instance x. An example of that would be that type 2 diabetes, for example, might depend on other factors. It's not just on obesity or whether somebody is overweight, but it could be on gender, on age, on plasma glucose, and so on. When that is the case, then you have multiple features x1 to xn, and probability of a person, probability of a data instance x is the probability of all of these happening, right? Probability of whether they are obese or overweight, and probability of their gender being male, and their age being 49, and the plasma glucose is 150, and so on. So that will be a person who is a male who is 49 years old with with a plasma glucose of 150 and is obese or overweight, right? So what are the chances of that person? That will be your probability of X. So assuming that they are independent, in probabilistic view, you can write them as each of them happening independent of the other. So it is just a product of each of these factors by themselves. So a person is male and aged 49 and obese and overweight and a plasma glucose of 150 by being can be computed by saying what is the probability that you find that you have male population in your overall population, right? Or what is the probability of somebody being 49 years old, or what is the probability of somebody being overweight, and so on. And actually not or but and what is the probability of somebody being 49 years age and the probability of somebody being male and probability of somebody who is obese or overweight and so and so. Okay, great. Again, if it's patient X is female, 40 years old, BMI 32, plasma glucose 150, and you need to classify this person as whether they are diabetic or not. So it's a two-class classification problem. Y equals 1 if they are diabetic, Y equals 0 if they are not. Then the naive Bayes way of doing it says that first you should know what are the chances of anybody being diabetic. So what's the probability of Y equals 1? And then what is the likelihood of a particular feature being what it is, the value being what it is, given the label is they're diabetic, or the label is they are not diabetic, right? So for example, what that means is what is the probability of this feature xi given that the label is 1, or the probability of xi given the label is 0. That would be your likelihood feature. And then if you know these two factors, then naive Bayes says that you are going to multiply the prior probability of y equal to y, that means probability of y equal to 1, let's say, and multiply it to the likelihood of all of these features being what it is for this given instance, given the label is y. So probability of xi given y is equal to y, multiply all across all the features. And then see which of the two labels, y equal to 1 or y equal to 0, maximizes this number. The label that maximizes this probability is the winner, is the label that you will choose. So let's take an example of how do you then train the model, and then use an example of how you will label an instance using that model. So this is your model. Your model says that you need to know this prior probability y equal to y and this likelihood of xi given y equal to y. How do you find these probabilities? Well, you have training data, right? So what probability y equal to y is prior probability. So you're basically saying of your data set, how many instances are class label 1 and how many instances are class label 0. The second one is you are estimating probability of a particular feature given the class label is 1. How do you do that? You basically count all the instances where the attribute is the ith attribute is xi in all the instances of class y, which means if you have 100 instances overall, 70 of them are class A and 30 are class B, then probability of first class y equal to A is 0.7, right? And probability of class B is 0.3. And then for estimating the second likelihood feature, of the 70 people who are in class A, find out how many have a particular feature and have a particular value in that feature. Okay. And basically you count that number, divide by number of instances of class y, that means 70 in our case, and that will be your estimate. So let's take so this is called maximum likelihood estimation, and let's take an example. This example is something that you have seen in our decision tree video earlier. This is a data set of 14 instances. There are 4 features: age, income, student, and health condition. And then the class label is yes or no, whether they will buy health insurance or they will not. All of these features are categorical features. So student is yes or no, health condition is fair or excellent, income is low, medium, high, and age is, even though it's a number, has been split into 3 groups: less than 25, 26 to 40, and greater than 40. So then let's take this new instance of somebody who is aged less than 25, income is high, and is a student and has a fair health condition. According to naive Bayes, how would you decide whether this person buys health insurance? So for that, first you need to know the prior probabilities, right? So recall, this is the formula that you will use. So the first one there is a prior probability. So you need to know what's the probability of anybody buying health insurance. So buy is equal to yes. There are out of the 14 instances, 9 instances were those that bought insurance. So probability of buy is equal to yes would be 9 over 14, and hence probability of buy is equal to no would be 5 over 14. Next, we are going to see the second feature, which is this likelihood feature of xi given y. For that, you're basically going to find a bunch of numbers. And I have just laid them out in a table, but let's see them one by one. So first is what are these columns? So you need to know what is the probability of age to be less than 25 given the label is yes. Okay. And the next number is what is the probability of age less than or equal to 25 given the label is no. So that will be just the first feature, correct? So in this case, looking at the 14 examples from the previous slide, you will see that of the 9 that are yes, that have bought insurance, 2 are age less than 25. So the probability of age less than 25 given label is yes is 2 over 9. And of the 5 people who have not bought insurance, 3 of them were aged less than 25. So that probability would be 3 over 5. Probability of age less than 25 given label is no is 3 over 5. You could do the same thing for the other features for this particular instance. So income is high given label is yes is 2 over 9. Income is high given label is no is 2 over 5. Student is yes given label is yes is 6 over 9, and student is yes given label is no is 1 over 5. And then finally, health condition is fair given label is yes is 6 over 9, and health condition is fair given label is no is 2 over 5. Great. So with these parameters, just that you have gotten just by counting the right numbers and dividing by the total number of instances in that particular class, you have all the parameters that you need to solve this particular instance, right? And how will you do it? You're basically going to multiply these factors together in the right way. So probability of buy is equal to yes given this instance is now going to be probability of y equal to yes, which is 9 over 14. That is coming from the prior probability. Then probability of age less than 25 given the label is yes is 2 over 9. Probability of income is high given the label is 2 over 9 is given the label is yes is 2 over 9. And same way, probability of student is yes given the label is yes is 6 over 9, and health condition is fair given label is yes is 6 over 9. So if you multiply these together, it is about 0.0141. You do the same thing for label equal to no, and then you find that product is 0.0069. Great. So then how do you use these numbers to decide what the predicted label is? what the formula is saying is the label is the one that maximizes this probability. So among the two probabilities that you have computed, the label that actually maximizes the value is the label. So between these two numbers, 0.0141 and 0.0069, the first one is the highest one, and so the label is yes. Okay, that's how you'll kind of compute. Great. So this example is naive Bayes also gives this label yes. If you recall, decision tree and support decision tree also kind of said the same thing for this particular instance. Excellent. So what did we learn? That so here we kind of saw how we can find the parameters just by looking at data, at the training data, and then just multiplying the right numbers and then comparing the two final products would give you the label, right? Why do these two numbers not add up to 1? They are both probabilities. Why should they not add up to 1 if there are only two options? Well, the answer is because they add up to actually the probability of this x. So these two are not the only two options, because they are the only two options for a given x. Probability of y is equal to yes given x, right? But naive Bayes does not have to model probability of x. That probability of x does not really change what your label should be, so you don't have to compute that value and do the division and so on, because if the number here is the 0.0141, if that is the higher number, that is going to remain the majority even when you do the normalization, and so it doesn't change the label. Okay. So for a naive Bayes classifier, how many parameters are there? Let's take the same example data set, the fact that there are 4 different features, okay, and then calculate it based on that. So first thing is you need to know how many prior probabilities are there. So there are 2 prior probabilities here. Label is yes and label is no, right? So there will be 2 parameters that you need to know. So we computed that they were 9/14 and 5/14 in this example toy data set. The next one is you're calculating likelihoods of each attribute given the class label, this probability of xi given y. So for that, you need to look at it feature by feature. So for age, you are actually having a lot of numbers. So for age, you have age less than 25 given yes, age between 26 and 40 given yes, age greater than 40 given yes. And then age less than 25 given no, age between 26 and 40 given no, and age greater than 40 given no. So for age itself, this combination leads to 6 different features. Because age has 3 values it can take, and label can take 2 values. Same way, income can be low, medium, or high, and label again can be yes or no. So again, there are 6 different numbers. You also need to know student is yes or no given label yes or no. So that again, that is these 4 numbers. And the same way with health condition being fair or excellent given label yes or no. So in all, you have 2 probabilities from prior 2 parameters for prior probabilities, 6 for age given label, 6 for income given label, 4 for student given label, and 4 for health condition given label. So in all, we have 22 parameters for this particular data set. If you are asked specifically about how many independent parameters there will be 13 independent parameters. I will let you find out which ones they are. Okay. Yeah. So I'll let you kind of figure out how that number is, and if you have doubts about that, we'll talk about it offline. Okay, So before we go, I want to kind of talk about what are the issues with naive-Bayes model. We in this data set we only talked about categorical attributes. What about numeric attributes? Well, for naive-Bayes, numeric attributes have to be converted to categorical attributes, just the way age was kind of converted. Okay, so you discretize the continuous variable or this numeric variable into buckets. What about missing value? A missing value where suppose you are trying to look for whether they are student or not, but because that you need that for a probability measure, but you don't know whether they are somebody student or not, then it doesn't really matter because you don't know that value, so you're going to ignore that particular feature when you calculate the probability. You calculate the probability without knowing that particular bit of information. Okay, so that's good. What about zero counts? Now this is important because you're kind of training or estimating all of these parameters given the data set. What happens if a particular combination never occurs? So for example, everybody in your data set had a health condition excellent. So this probability of health condition fair given label yes is never happens. Okay, or even if there were some, everybody some who had fair health condition, everybody who had fair health condition, let's say, did not buy insurance. Okay, so this probability of health condition fair given they bought insurance is zero because nobody in your data set had that. What happens is because the probability then will be zero, any number, anything else will actually, because it's zero is multiplied to everything else, it will give you a zero as your final answer. So that's a problem. Because even though you have other strong indicators, just because your data set was limited and you never saw this example, you are going to get a zero probability. So to overcome that, the preferred way is what is called smoothing, where you add a dummy count. You assume that there is at least one person for any bin, for any combination, any probability that you want to compute. Okay, there's at least one person. So by giving that dummy count, that additional count, you make all probabilities non-zero. It will be a small value, but it will still not be zero, and hence you can still see whether other very strong features can overcome this fact that there was one particular feature that was very rare. Okay, so Laplacian smoothing or add-one smoothing is the way naive-Bayes models overcome that zero count problem. Okay, so just to kind of summarize, the key takeaways from this classifier on naive-Bayes is that it's very easy to implement, it's very efficient, and it kind of typically gives very good results across multiple tasks. So it kind of provides a very strong baseline. The only downside is that it has a strong assumption on features. The fact that these features should be conditionally independent given the class label, that may or may not happen. Was most likely in medical field, these features are kind of related to each other. And so this assumption does not hold. But even with that, this still provides kind of a very strong baseline and should be first kind of attempt on for any kind of supervised machine learning model, kind of should try this one out as one of these kind of strong baselines.